All right, hello everyone. How many of you, by show of hands, think that developing user interfaces is easy? All right, nobody raised their hands, which is great because I was going to call you out if you did. But my name is David Khourshid, and I love working with user interfaces because, in my view, I think it's one of the most creative parts of working with web technologies or just technology in general. And that's why I do it every week, or almost every week, on this screencast called the Keyframers. So me and a friend, we do these complex dribble animations. We take them and we try to create them into real-life animations with HTML, CSS, and a little bit of JavaScript. So I also work at Microsoft, and I'm on the consumer software engineering team. And if you're not familiar with this company, I have a translation over here. But Microsoft, it's known for its it's known for its user interfaces, right? Here's the thing: developing user interfaces is hard. I mean, we're still trying to find the best ways to do it right, and it doesn't matter if you're doing it on the web or you're doing it like with embedded software. It's not easy. And so I think that one of the reasons it's so hard to do is because of time. Time is this variable that we tend to ignore in software because when you're working on an app, everything happens in time. However, the way we develop, we have so many different ways of dealing with time. You know, we have callbacks, right? We have promises, which are sort of better than callbacks, but still it only emits one value. We have a Cinco wait, which is one of my favorite features because it's very close to C#2. And we also have observe a balls, which this is my favorite way of dealing with time because it deals with time in a stream of events. But we're not going to talk about that exactly today. I want to tackle the biggest problem with dealing with user interfaces, which is dealing with how state changes over time. So let's take a very simple application. I have a button. You fetch data. You press it, you fetch data. So you click, you have a pending request, and eventually you get your data. But what happens if this takes a really long time, right? So you want to show some sort of a loader when that's happening, and then, after a while, you get a response back. But that's not good enough. And I'm sure that some of you have done this, and you know exactly where this is going. There's still many ways that this could go wrong. For example, let's say you have an irate, impatient user. You're clicking fetch data, and they decide, I really need my data. So for whatever reason, they think that clicking the button many times will somehow get their data faster, right? But you're like, I'm a developer. I'm smarter than them. I'm going to disable the button, right? Which, I mean, that works, right? But let's say that, the user is let's say that she's angry, but she also knows how to use the dev tools and unblock that button. So let's illustrate this in code a bit. This is a sort of React code because it's using setState, but you could sort of envision this for pretty much any framework or even no framework at all. Like, let's say that we're trying to mimic this button's behavior and do a search for, let's say, Flickr images or something. So pretty easy. We do a fetch request, and once we get our data, we show it. But of course, we want to show a loading screen, right? And so once the data comes in, we have to remember to hide the loading screen too, or hide the little loader so that it's not showing when our data is, showing. But then we also have to keep in mind what happens if there's an error on the screen too. And then what happens if we actually want to, retry, or we want to cancel the request, or just, there's so many different things that you have to think about with a single event. So this is just a search event, and we already see the complexity here. Can you all see that? Here, I'll zoom in for you. This is a complex problem, and it's because we tackle this using what's called the bottom-up approach. And this is also called the event action paradigm. So this is what I mean by this. When we do an event, like on-click, or on-tap, or on-press, or on-key, key up, key down, whatever, we put all of our application logic inside of that event. And that's a problem, because these actions that happen inside the events handler, these are the ones that change the state. And so these become very, very hard to test, because we're not sure what's going to happen when. We have to organize our logic between event handlers. It's also very difficult to understand. If you try to show your app to another user, or even a designer or someone who's not technical, then it's going to be hard to describe what all the features, what all the capabilities are of your application. And it will contain bugs, and this is just an unavoidable fact, because there's so many different ways that you could handle events that you're going to miss one edge case, guaranteed. They're also very difficult to enhance, where once you have all that logic inside your event handlers, then it becomes really hard to add new features or change the behavior of your app. And features, of course, make it worse, because it just increases the complexity. So here's the intuition. First of all, we have to realize that user interface components are not independent of each other. We can't treat them like they're their own units. They communicate with each other, and they don't necessarily fall in this nice hierarchical tree structure like React or Angular or Vue would want you to believe. Instead, we have to communicate across components all the time. Also, actions are based on events and states. And what I mean by this is, let's say that I have an on-click on the fetch button, or the search button. That has to do something different depending on if I'm already doing a search, or if I have not performed a search yet, or maybe if the user is allowed or not allowed to do a search. And so we realize that the event action, or the bottom-up paradigm, is just too simple for our needs. So how can we better model the behavior of our complex user interfaces? And so this is what brings me to finite state machines and state charts, which I absolutely love talking about. But of course, if you try to look at it on Wikipedia or something, you're going to look at some really, really complex definitions, unfortunately. So I'm going to break it down. And I'm sure that many of you have either learned this in university or heard of it before. But we're going to talk about how it applies to user interfaces today. So finite state machines are comprised of 5 parts. First, you have an initial state. Then you have a finite number of states that follow from that initial state. And so that's an important part, where your app could be in one of these finite number of states. You have a finite number of events that the user could do too, or events that some outside source or some internal trigger happens. You have a mapping from one state to another based on these events. So for example, if you're in the idle state and you perform a fetch request, then now you transition into the pending state. And you also have a finite number of final states, which they sort of depicts that your app is in a completed state. But mostly for web user interfaces, that's not entirely the case. So let's model our button where we're fetching data in a visual way. So this is pretty easy to understand, whether you're a developer, designer, project manager. You could clearly see everything that's happening and everything that can happen from this diagram. You start in the idle state, and then depending on what the user does, you move between these different states of your application. Now there's 2 ways that you could code this. Of course, you could just use switch statements and switch between which state am I in and which event happened, and then decide on the next state. But my personal way that I like to do it is by using sort of a JSON structure. And I like using a JSON structure because it's easy to just have a lookup function. You're looking up the state, you're looking up the event, and from that, it's like a dictionary, or a double dictionary of sorts, where you get the next event. And so in this example, we have, let's say we're on the searching state, and we have a resolve event. Then we go to the success state. So the way that we could interpret this state machine is we just keep track of the states. So in this simple example, which, it's not even a library, it's just a JSON object. You keep track of the state, and then you send events. And so each one of these events is going to transition the machine and determine what the next state is going to be. So one of my favorite quotes from your MC is that any sufficiently complicated model class contains basically part of a finite state machine. And I see this actually most often in state management libraries, such as Redux, MobX, which, I mean, these are excellent libraries, but I'm sure that you've also seen in the whole landscape, even with Vue, Angular, whatever, is that there's like 101 different ways of handling states. And all of these, once you realize like what state machines are and how they could manage your app state, you see that they're partial implementations of that. So here's an example where I use the finite state machine to create just a simple app, and this is a Flickr app that we were talking about. So if I search for something safe, tapas. All right, so those tapas came up, but if I press cancel, then naturally, they're not going to reload. And that's because when I'm in the idle state, or the gallery state, there are no outgoing transitions from search. And so naturally, I have this control of what events are allowed to execute and when. And then so, going deeper, we could, those are people enjoying their tapas. And man, these look good. Anyway. And so here's another example where this is just a login form, and we're just going through, let's see, password is password. So if I type in the wrong password, no matter how many times I click submit, so you see I pretended it was disabled, but it's not really disabled. It's still going to perform the behavior that I expect because of the natural way that the transitions are defined. And then finally, we could just have the correct password. So they're very useful in animations too, and that's why in the keyframers that we do weekly, we use finite state machines. But I don't want to present finite state machines and state charts as just another way of writing your state, because there's already 1,000 ways to do that. But instead, I want to show you that you could use these to generate integration tests, which are some of the most painful tests to write, but some of the most important as well. Because if we represent our application as a graph, then we could trace through each of the states. It's just like, Google Maps or something where you're just following a path until you get to your desired state. And so you could do something like shortest path algorithms to find the shortest path from your initial states to any of your other goal states. And so these represent all the happy paths that your user could take. And these could also be automatically generated, given one of these algorithms. You could also use what's called simple path algorithms. And what these do is they just make sure that you don't visit a state twice. And so that's going to generate a lot more paths. And so this is going to be good because this is going to show you all the possible edge cases that a user could take through your application. And one of the criticisms of this is that it's going to generate a ton of different paths, but in my view, that's sort of the point. You want to capture every single possible thing that could happen in your application. And then you could use these to automatically generate tests. And so, we could manually test the code, right? Or we could write just hundreds of unit tests and integration tests by hand. And this is sort of where we're at today. But by modeling our software and our user interfaces, we could actually, whoa, I'm not done yet. Why'd you go there? Hold on, don't look, close your eyes. This state machine is broken. All right. Well, yeah. So you could generate tests, that's the point. You could also use state machines for analytics as well. And so I did this in the previous project where if you use VS Live Share or Visual Studio Code Live Share, then I added telemetry where we modeled parts of the application as a state machine, and then we were able to trace what are the most common paths that the users took. And so we could visually see through this generated D3 diagram we could see which are the states that users most commonly visited, and we could see if users are running into errors, and then we could narrow it down by what type of user is running into error, what are they doing before they run into this error state. So using state machines for analytics is also really interesting because when you have these weighted diagrams where these weights represent just more people going from state A to state B to state C, then you could start to see sort of desire paths where it's obvious in this diagram that people want to get from state A to state C, but unfortunately they have to go through the step B. And so instead, we could analyze this and conclude that it might be a good idea to provide a transition from state A directly to state C, and that improves the user experience. So software bugs are also made very, very clear by looking at diagrams, whereas they might not be as clear in code. So for example, this simple finite state machine for modeling a loading request, there's one problem with this. We did not model what happens if there's an error. So we add an error state. And then we do this, and then we realize that when we're in this failure state, what's supposed to happen? Is the user just stuck there, forever? You wonder why IT people say restart your machine? Because this happens. And you're stuck in this failure state, and you don't know what to do, so the only thing you can do is restart your machine. Instead, we should provide affordances for the user to go ahead and retry the request. Now, one important question is, does this kind of software modeling scale? No. But it's still a good idea. This was solved, though, thankfully, 30 or so years ago by a formalism called statecharts. And what statecharts are these finite state machines, but extended, where they solve all of the potential problems that we're going to see with just modeling your software as pure finite state machines. So statecharts introduce the notion of actions, because your software needs to do things. It needs to, for example, when you enter a state, you might have actions, or when you exit a state. There's also the idea of guards, where you should use these sparingly, but they sort of guard transitions, making sure that certain transitions only happen when conditions are met. There's also hierarchy, so you could nest these state machines inside each other. And so they exhibit the behavior of their parents, where if you're inside of a child state, then the event goes to the child state first, and then if the child can't handle it, then it goes to the parent. If that sounds familiar to you, then it's exactly the same idea as events bubbling and propagation. There's also orthogonality, which I hate using that word. It's just to make people sound smart. This is just parallel states, states that happen at the same time. And there's also the idea of history states, which is extremely useful because dealing with history is hard. And yeah, so here's an example of where parallel state machines can come into great use. Let's say that you're trying to model a toolbar for selecting a font style, where you could choose bold, italic, or underlined, and you could toggle between each of those. If you were to model this as just a finite state machine, you would have to go through you have to multiply the bold states plus the italic states plus the underlined states, and so you get 8 different states. Add another one like strike through, and then you get 16, and then it exponentially increases. So instead, we could model our diagram like this, where we just have these orthogonal regions, and we say that these states don't affect these states, and these states don't affect these states. And so this scales much better than having that Cartesian product of states. Hierarchy is also good for simplifying state machines as well, where something like this could get complicated really easily, but we see that there's shared behavior between success and failure states. So we could just have a shared state called searched. And then from this search state, we could have a search action that lets the user retry whether they're in this success or failure child state. So I created this library called xstate, which allows you to create these state machines, and it uses the exact same structure that I showed a few slides back that required no library, but this allows you to add things like actions, guards, hierarchy, parallel states, and also history as well. And the way that it works is just like we showed in the previous slide. We have a transition function. And that transition function is just like, for example, your Redux reducer, where you have a state, you give it an event, and all it does is return you the next state. So it's a pure function, and it's up to you to decide what you do with that next state. But apart from the next state, it also returns you which actions you should execute, which is extremely helpful because if you take a look at Redux, Redux only gives you the next state. And that doesn't do much because you want to also be able to execute actions, and that's why we have all of this middleware like Redux Saga, Redux Observable, Redux Thunk, in order to deal with these side effects. And so this just naturally gives you the actions in what's called declarative side effects. So here's an example using xstate where I have that machine modeled right down here. So I have this JSON object, and so this JSON object represents the behavior of this application. It's sort of like a week designer, where you have like Sunday through Saturday, and you could sort of select days. Let's see, select days. You could drag them, delete them, and make your Sundays really long. So this is based on an animation by Gal Shear, by the way, and I really wish that something like this existed. But yeah, so there's a lot of advantages to using state charts, especially over state machines. For one, NASA, a few years ago, actually many years ago, when they were designing the Mars rover and they needed to launch it over to Mars, they used state charts extensively to not only model the software, but also to generate the tests, generate precise diagrams so that they could share it with stakeholders, generate code, actually, which is a little bit of a scary thought, but it makes sense in terms of getting as fast code as possible, and also accommodating late-breaking requirements changes. I mean, these are the things that cause you to stay past 5, up until 10, 11, midnight, just working on these last-minute changes that are requested, because your application is so complex that you don't know what changes are going to affect what. But when you have a clear diagram, it becomes much easier to do so. Of course, there are disadvantages too. For one, it's a learning curve. Learning state charts is not really the easiest thing in the world, especially if you try to read the historical papers on it or the Wikipedia entries as well. And modeling requires planning ahead. So that means you can't go into hackathon mode doing this. When you want to design your app as a state chart, then you have to sit down with pencil and paper. You don't even touch your computer, don't touch your keyboard, just start drawing boxes and arrows and model your states and transitions like that before you even start coding. And I know a lot of you like to just jump right into the code and start hacking away, and this sort of forces you to do the opposite and to model your software first. But in my view, there are complexity trade-offs. You can't really see the finite state machine, but that's the yellow line. And so that starts off very simple, as we saw, but we also saw that it increases in complexity exponentially. Using the bottom-up technique, the more features and the more complexity we add to our app, the more the code becomes complex. However, with state charts, even though you have that initial complexity of designing your application, adding features becomes easy, and removing features and also changing the behavior of your app becomes easy too, because you could see it visually. And so speaking of visually, I do have the state chart visualization tool called xStateViz, and I'll show it to you in a minute. But basically, the JSON structure that you put inside your machine, you could just copy and paste that into this tool. And actually, I'll go ahead and show you. And so that JSON is automatically generated into this diagram. So this was the Flickr search engine diagram that we saw before. Sort of had to drag a few things to make it look clean. This was what was copied into the machine. And then if we go over here, we could actually simulate our machine and be able to play around and make sure that everything, including the actions and the state transitions, are happening the way that they should. And this is the exact same code that's used to power our application. So let's see, where was I? So there are places that are using it, which I was really ecstatic, to find out, using XState and the visualization tool. One of them by Ryan Florence, you might know him in the React community. He has a site called workshop.me. He has a pretty complex payment form, and he decided to model it using XState. And what was really cool was I found this out on Twitter. I immediately went to the site and started searching through the minified code for this JSON structure, and I copied it into this tool, and I was able to visualize it just like that. And so I was excited about that. And then something that I discovered literally 2 days ago was this tool called Vault.io. I think it's called, or vaultproject.io. And this is made by HashiCorp, the same company that does Vagrant. And so what they did was they have an interactive tutorial on the right-hand side that, depending on which state the application is in, it shows contextual help for the user and helps them decide, how to accomplish their goals, which is really, really, really cool. But I am releasing a version 4 of XState, which has a whole bunch of new features, such as external states. And so this was a really big one. External state is sort of the state that doesn't fit in your finite states. It's sort of those dynamic states. Thankfully, this is also modeled by a spec that was created almost 10 years ago. And so it allows you basically to do the same thing as Redux or MobX or anything like that. I'm also introducing delayed transitions in events for you to better model what should happen after a certain amount of time. And also an interpreter. So with XState, you could model your state machines and state charts any way you want. And so that includes, you could use RX, you could even use Redux or MobX to interpret the state machine. But I also have a built-in interpreter where all you have to do is pass it in a machine, initialize it, and then start sending it events. And then you could listen to those state changes. There's also SCXML conversion. So by the way, this is in beta, so you install it at XState at next, so it's not final, it's not version 4 yet. But one thing I'm working on is SCXML conversion. And so this is not really a human-readable format, but it is a standard, a W3 standard that's used by big software tools such as Qt and Yakindu, which both of them have nothing to do with JavaScript or the front end, but it's really cool where you could make things and model your application logic in XState, have that converted to SCXML, and then use it in languages such as C#, C++, Java, Python, and more. And also, there's the idea of final states as well. So if you ever wanted to model things like promise.all, where 2 requests have to complete, and then once they both complete at whatever time they complete, then you send a signal that says, hey, all of the requests completed, then that's what final states are good for. So I have a bunch of resources and tools here, but I wanted to show you a quick demo, which this is going to go terribly wrong, but I'm excited about that. So I created a simple tic-tac-toe machine game that models a tic-tac-toe game. And you might be thinking, OK, this is a pretty simple application. You've probably made it before. And I just want to do it to demonstrate both some of the new features of XState and also why you should model your software because of the other advantages that maybe just using Redux or RxJS or MobX can't provide alone. So I'll zoom in here. We have an initial playing state, which means that we're starting in this playing state. And on playing, when the user plays, we transition only if it's a valid move. And you'll see that these are strings for a reason. And of course, we have an action of updating the board, which is our external state. And so this is going to loop and loop through this play state, which we'll visualize soon enough. And every time it goes through here, we check if there's a winner or a draw. And so you might be thinking, how is this going to work? This is all JSON, it's all strings. So we have a winner state over here, and that's where we set the winner. And then we have this draw state. So here's the magic. We have these actions over here, and this is one of the new features of Xstate version 4, where we have this assign action, where, for example, updating the board, we set this array of 9 values, because tic-tac-toe is 9 squares, so we set the event value to the player, and then we return the board. We increase the number of moves made, and I'll show you why that's important. And we also set which player is next. So if it was X, now it's O, and other way around. And then set winner is simple enough. It just sets, who was the last player, then the other player is the winner. And then we have these guards like check win, where we're just, doing a simple checking each row, each column. Things that you would normally do if you were creating this on your own. And so we could see this actual game running over here. It's a React app, and you're not going to be impressed by this at all. But it's a tic-tac-toe game, and it actually works, which, okay, I did a draw there. If you look on the bottom right, you could see that because I modeled this as a state machine, I could actually visualize, this is a terrible player, I could visualize what the state is and what the external state or the context is and all of that. So you might be thinking, okay, the visualization stuff is pretty cool, but is that really all that you could do? So I'm glad you asked, even though none of you asked that, because I'm going to show you. Because this is a graph, a directed graph, we could analyze this graph. And not only could we analyze it, but we could parse it and generate the things I was talking about. Shortest paths, simple paths, weighted paths, things like that. And so I'm doing this over here. I have this get shortest value paths. And the reason it's called value paths is because I'm including the external state into these paths. So over here, I'm filtering them by if there's less than or equal to 5 moves. And that's just so that we don't get a huge number of paths, because this does generate a lot of paths. And then I'm filtering. I'm looking for the winning paths. So I'm looking for where the value is winner and the winner is X. And so this is just a very simple filtering. We're taking each of those paths and we're narrowing it down. Then from each of these paths, I'm running Puppeteer, and I'm mapping this play event to clicking an actual square based on what the event is. And so we could see, if it works, that's automatically going to generate every single possible path where X wins in less than 5 moves. So, I mean, if you want integration tests, how about a few hundred automatically generated for you right there? And so you could see how you could apply this to more than just, a simple game. And okay, let's quit that. And so, you could create tests where you could say, and context.board 0, where X is not the first square, right? And then so it will regenerate those paths, filter them, and make sure that it chooses paths where X is not the first square. And I'm not giving it any special logic telling it this is how a tic-tac-toe game is played. It has no idea. All it knows is this is a state machine or state chart, and I'm just tracing the paths, trying to find the goal path that you want me to find. And so you could see that it's very easy to create integration tests just based on that. So I guess there wasn't that many, so that's good. So anyway, my goal here is to show you that your code can do more than just running your application. Your code can generate tests, it can improve your user interfaces, and make them more robust and state-of-the-art. So thank you so much, Barcelona.
What I saw was that there's this additional thing which people may not be initially familiar with, which kind of formalizes what's happening in a stateful user experience. And because we had this formalism, we were able to build some tools on it, much to draw an analog to maybe something like type checking or something, where you can do some automated things. You gave us an example, the integration tests that have been, that gave you an additional sort of affordance for it. Could you maybe give an idea, once someone gets into it, when they get familiar with it, some other surprising benefit they may not be expecting from being able to work with state charts from your own experience? Maybe not the first thing, but after sort of you get going with it?
Well, I mean, from the integration tests, like what I saw was something I didn't mention is that the integration tests are using the exact same machine code, right, as the actual application, which means, I mean, you all know how painful it is to write integration tests. Changing even one single little feature or adding something new in your app can invalidate all of your integration tests. But with these, since they're automatically generated, they're just regenerated again. And so something that I'm working on and doing research on...
Whoa.
Sorry.
You mean that you make a change to the code and you don't have to manually change all 500 integration tests? I'm sold.
No,
I'm sold.
All updated. But also, one of the things is the analytics part of it too, where you're analyzing going from state to state. I remember manually making those funnel charts where you had to painfully do those, the Google Analytics for every single possible path. But with this, it's automatic, and then you could visualize where your users are going to most and how long they're taking between each state. So,
So I'm going to be a hero to my user experience team and my marketing team at PagerDuty if we adopt state charts for our user experience.
Yeah.
I was already sold. Why do you keep selling me? David, this is really great technology. Folks, look this up. I have done some research into this. I was very impressed when I saw it before. This is the kind of thing which is literally a step ahead of where we go. When we first started writing programs, people just made stuff, had go-tos. Then we developed structured programming. We developed functional programming, object-oriented programming. Each step along the way taking us to a new level. I feel like in user experiences, this type of technology is again one of those advances that helps us move past a sort of more primitive state. Thank you so much.
Thank you.